Okay, hi there, everyone. I'm Shannon Hilsey.
Dave Bowie, nice to see you.
Camera.
Yeah.
Um, Francesco's asked us to talk to you about structural elements in the context of landscape architecture. He kind of mentioned that a little kind of recap or outline of what structure means, even. We're not going to get into any math, we're just going to outline the things that the engineers are thinking about. And then we're going to talk about what structure looks like for a lot of the landscape elements. This is a very practical lecture. There's a few pretty images, but mostly it's about how do you detail things? What do these things look like from the point of view of the structural engineer? Because a big part of that is you knowing when it isn't your scope and when it is. Because landscape architecture is this funny zone where there are a lot of elements that you're responsible for drawing and detailing, and that at a certain point, it becomes the responsibility of the structural engineer. And I find sometimes in projects, landscape architects can either do too much of it on their end or sometimes not enough. And that's all simply because you guys aren't used to knowing when that line is. So it's no fault of your own. So we're here to kind of help talk about what that line is. So just a quick kind of thought about what structure is and what we're talking about. I always say in the structures curriculum for the architects, because that's what I teach, is that everything you need to know about structural engineering, you already intuitively know. You know when something seems too small. You know when something seems too big. You know when something is going to fall over. And I spend a lot of time teaching them how to stop thinking about it, and they kind of lose that intuitive sense. So it's important that you remember your instincts on these things. But your big problem is that a lot of what you're doing that is structure is underground. So you don't have that tactile experience of knowing what it looks like. If you went into a 50-story steel building and saw a column that was just this big, you would know that that seemed kind of tiny. But a footing for a retaining wall isn't something that you have a real sense of because you don't see it. It's buried, it's hidden. So we're going to show you a few images so that you have a sense of what it looks like. Because I'd say that's probably one of the number one issues that we see come up is that kind of in the tender process, retaining walls, for example, aren't drawn big enough and they end up being underestimated, and then an extra is needed kind of during the construction phase. Okay. What we're talking about in structural engineering is statics. Really, that means, if you want the technical definition, the branch of mechanics that is concerned with the analysis of loads, so force and torque or moment, on physical systems in static equilibrium. That is, in a state where the relative position of subsystems do not vary over time or where components and structures are at a constant velocity. What does that mean?
Doesn't move.
It stays still. That's all we want. We don't want our object to move. It can deflect. That's a different thing. When we say not move, we mean not fly off into space. It's allowed to deflect a little bit and respond to the loads, but that is something different than moving up and down, side to side, in and out of the page, or rotating in any of those directions. So we know that every object has loads acting on it. If there's loads acting on it trying to make it move and we want it to stay still, what must be happening? It must be in equilibrium. So for it to be in equilibrium, we need equal and opposite reactions that make it stay in place. So each structure is subjected to a series of loads that try and move the structure, such as self-weight, loads, wind loads. We want the structure to not move or remain in equilibrium. To remain in equilibrium, there must be an equal and opposite force to keep it in place. This is called the reaction. Would you like to demonstrate something, Dave? That was not an
Not
equilibrium.
an equilibrium.
I think where Dave is going is that when it's balanced like this, it's in equilibrium, but it's a precarious equilibrium. We know that the slightest load that way causes it to move in space. And so for it to be in equilibrium, if I'm the applied load, Dave, can you be the reaction? Can you be the reaction? I'm the applied load. Can you be the reaction for the load I'm applying? Where would you put a reaction?
I didn't know what.
So now, for the load I'm applying to stop moving it, Dave's finger would become the reaction. So everything needs an equal and opposite reaction to make sure it stays in equilibrium. Again, this is all stuff you intuitively know. I'm just putting words to it that may or may not confuse you. Okay, I'm going to make myself smaller here so that you can see more of the screen. Really, the things the structural engineer looks at are strength, stiffness, and stability. Strength is the amount of load a structure can sustain prior to failure. So that means some sort of massive failure. Stiffness is the amount of force required to make a structure deflect by some fixed increment. So that's deflection, for example. And stability, worst definition in the world, the state of being stable, or the opposite of unstable. We know that for it to stay still, it needs equal and opposite reactions. If it does not have those equal and opposite reactions, it's not stable. So that pen,
Stable?
stable, not stable.
Unstable.
You, more than almost anything, intuitively understand stability. If you want to climb up a ladder, you know what to do with it. You intuitively get stability. And somehow when people draw things or start to design them, they can have that kind of intuitive sense disappear. So it's always important to go back to the basics and think, do I have something that stops this from moving in all of the directions and from spinning in all of the directions? And if you have that, you're going to have a stable structure. And as engineers, we do this for every connection, every element, and every system in a building. So strength, stiffness, stability, every connection, every element, every system.
No, so talking about stability and your intuitive knowledge of it, I spent a lot of time on ladders in the last couple of weeks.
We've been building things.
And a ladder, you've leaned it against the wall like this. And I realized that as I start to climb the ladder, I hug the ladder really close when I am on the lowest few rungs. But when you hug the ladder close, your knees are banging on the rungs and it's not comfortable. And that the farther I get up the ladder, the more I hang back off the ladder, because I recognize that intuitively that if my center of mass is inside of the point that it's bearing on the ground, it's stable. But if I'm down here and I hang my weight out, the ladder will tip. Up here, if I hang my weight out, it's still inside the center of rotation. And I found myself doing that intuitively last weekend.
Yeah.
I wasn't thinking about it. I just know that when you start up a ladder, you hug it close, and the farther you get, the more you can hang back.
I think a better one is that most people, if anyone skis or snowboards or skates, you know intuitively, and obviously you're moving, so we're not talking about that motion, but tipping over, you know that if you crouch down, you're more stable. So intuitively you have this sense of what's going to keep you stable. You know that if you're standing up and someone pushes you, the best thing to do is to spread your legs a little bit to stop that from happening. You intuitively know how to remain stable. Okay, so let's look at each of those three things. So strength, stiffness, and stability, just briefly, and then we'll kind of jump into more practical things. And in 15 minutes, I have to leave to pick up our children, so Dave will take over.
So then we will talk about shadow.
So strength. all of the factored loads that we put on a system need to be less than the reduced capacity of the system. So basically, we say if we load it up, it needs to be strong enough to resist all of those loads. But just to make sure we're being extra careful, we'll say here are all the loads and we'll increase them a bit. And we'll say here's the material and it's got a capacity. Let's just assume maybe it's not as strong as it could be and we reduce it. And then that reduced capacity needs to be greater than those factored loads. And if we have that, we will have a strong enough system. This is a life safety issue. Okay, this is non-negotiable. This is something that we have to make sure happens. And when we're doing that, we think of all of the load combinations of dead, live, snow, wind, earthquake, temperature, soil, pre-stress, all acting as either axial loads, so that means squashing it or stretching it, shear, or bending for bending moment. So this would be bending, for example. And we need to think of all of those combinations on all of those types of actions on the element and make sure that it is strong enough to resist those loads.
Colloquially speaking, we're all very comfortable with the idea of a factor of safety.
Yes.
We used to use factors of safety, and that was a technical term within the building code. We don't anymore. But now what we're doing is we essentially have two factors of safety. We have a factor of safety on the applied loads and a factor of safety on the strength of the material. So we have two factors of safety that combine.
Yeah.
So when Shannon's talking about factoring the loads, it's a factor of safety, and the reduced capacity adds a second factor of safety. Strength can be a number of different things. Strength is fracture. So that's easy to imagine when something literally breaks. Strength can be bending to the point where it's no longer usable. So with ductile materials like steel, they can bend to the point where they're no longer usable. That's considered a strength failure. Did you?
I took those slides out just because we're talking about strength, stiffness, and stability.
Yeah.
I didn't want to talk about the crossover between the elements. But if anyone has ever taken or wants to take my core architecture classes, we talk a lot about that crossover and what happens in the play between those things. So, stiffness. How much does an object deflect under those same loads? So what happens to the object, kind of not movement in space, but small movements within the system? This is all about human comfort and preservation of finishes. So preservation of finishes, we don't want drywall on our ceiling to crack in a building, for example. If somebody's standing on a bridge and someone else is running along it, we don't want them to feel disturbed. If you're walking yourself across the bridge and it deflects a lot, you don't feel comfortable with it.
We could add the word non-permanent to
non-permanent movements.
Yeah, recoverable deflection or recoverable movement.
So this would be vibration and shrinkage of certain elements. So wood shrinks and concrete shrinks. Stiffness is actually a big part, or the kind of the things that are incorporated in that end up being a large portion of what governs design. We make sure it's strong enough, and then usually stiffness ends up governing. So we tend to check a multiple different things.
The stronger the material is, the more likely it is that stiffness is going to be the thing that controls. Because the stronger it is, the smaller it can be, and the smaller it can be, the more flexible it will tend to be.
Yeah, so steel, for example, is a really strong material, so we don't need a lot of it, which means it deflects more, which sounds totally counterintuitive that the stronger material is more susceptible to deflection, but it's because it's so strong we don't need as much.
And what's the most rigid material you can think of? Quick, it's concrete, right?
Of course,
Concrete's
obviously.
weak.
Concrete's not very strong at all.
That's why it's so rigid, because it's massive, because it's not that strong.
So stability. This is where you think about, is there a reaction to resist the loads in any location they may be applied? So this was a really good one when Dave was talking about climbing up the ladder. the way he positioned himself changed depending on where he was on that ladder. So that ladder, you need to think about the load being applied here, here, or here, anywhere along its length. All of those need to be considered, and we then need to go back and think about that load and all of those conditions for strength as well. So there's a lot of things that the engineers are checking. All that to say that for a lot of what you guys are doing, most of it is not really governed by structural design. And that is kind of the biggest challenge you guys face. And I find a lot of times landscape architects will say to me, can you design this for me? And I have to say, it's not structural. I can give you good advice, but it's not structural. So what I'm saying isn't it already works in theory. What can you do to make it a little bit better?
Yeah, there's no criteria.
There's no
against which
criteria
to evaluate it.
Yeah,
right?
exactly.
I was going to say on stability, you know, we talk about tipping stability. That's this one, you know. Oops. But someone might acutely say, I thought buckling was stability. And buckling is stability. There's all kinds of different stabilities.
Buckling is, we know that this paper can't hold a compressive load because it's so thin. It's actually so thin I can barely make it buckle. It buckles. Actually, this is a good one. My foam block. If I squash it, it buckles.
So the commonality amongst all the different stabilities is a feedback loop. So the tipping, the farther the load gets this way, the more rotational force it has. That's a feedback loop. Buckling, the more it curves, the more bending there is, the more tendency there is to curve. There's a feedback loop. So that's what stability is a feedback loop that doesn't converge.
Okay, this probably is beyond what you guys wanted to talk about, but I'm going to give you 3 quick slides for the 3 main structural materials that we use with just a little bit of data on them. It's not a lot. Some of it's technical data, and some of it is just good thoughts and practices about that material. Again, in my normal courses, each one of these gets 2 whole lectures. So 6 hours of me talking. So this is very, very condensed because you're getting it in 3 slides. Okay, so wood, steel, and concrete are the main materials we tend to design with. Obviously, there's a lot more. There's rammed earth, there's straw bale, there's glass, fabric. There's all kinds of different materials, but these are the 3 main ones. So steel, you heard us say that it's strong. You also heard us say it's not stiff. So why do I say that it's stiff here? The material itself is quite stiff, but because it's so strong, we need so little of it that it appears to not be stiff. So if you made a steel slab that was the same thickness as a concrete slab, the steel slab would be stiffer than the concrete slab. But why would we make that steel slab when for strength, we only needed a thin plane of it? And why waste money if we don't need it? And so that's when the stiffness of that steel slab might start to govern. Steel has great quality control. It's made, there's a bunch of chemists making it in a plant. It looks very rough, but it's highly precise kind of chemical reaction happening to make steel. And then when it's being fabricated, it's being made in a shop. So there's not people outside in the cold and the heat and the rain. They are in a big building working under controlled environmental conditions, able to go back and reassess and look at what they're doing. So we have really good quality control on steel. Steel is isotropic. That's another word that some of you may or may not have heard, but isotropic means it behaves the same in every direction. If you had a cube of steel, if you squashed it this way, or this way, it would behave the same. That is not true of all materials. Steel needs a lot of lead time when we work with it. So if you're designing a steel pergola or a steel stringer, it takes some time to get it to site. So they need to create the structural drawings. It needs to go out to a fabricator. They make their own drawings. Everybody looks at them, makes sure that they're right. Then they make it in the shop, bring it to the site and install it. But once it's there, it goes up really fast. It has a specialized workforce. That's another con for it, that you have to have people that are trained in working with steel. So how does steel fail most of the time? This is a slide from a very specific lecture that I do. So this is maybe not as applicable to you guys, but beams tend to fail in bending, but are often stiffness governed. So how much they deflect tends to govern them. And that's all about how comfortable do people feel on it.
We should say that steel doesn't fail most of the time.
Yeah.
So there's almost a false premise in the statement. That is, what is the controlling failure mode for a designer?
That's a good point.
But in fact, steel is very reliable. It's generally designed well and rarely fails.
Steel columns, if they were going to fail, or the design mechanism we're worried about most of the time, is this aspect of buckling. Because they're so strong, they can be quite slender, which means they tend to be governed by buckling. Wood. Wood is organic. I mean, it literally is a tree that grows in the forest. So somebody goes in and cuts it down. We know that trees have branches. There's different types of wood. How it grows can vary depending on the season, location, whether there was a bug infestation one year. All of these things have an impact on the wood. So that means there's lots of factors that we have to apply to it. But we're pretty good at it. We have a system, and we lump them into categories, and we say, okay, let's think about this aspect of wood and make a factor for it. And we'll just add it to our design. There's an easy workforce. If I wanted to invite you all over to help build a deck in my backyard, maybe I'd bribe you with pizza and beer, and you'd all show up and could help me build my deck. You do not have to have specialized training to build in wood.
That is a fine plan. Let's do that.
It's fast construction. You can go to Home Depot, buy the lumber you need. Now, I'm not talking mass timber here. And I think most landscape elements probably would not involve mass timber. That's more along the lines of steel construction. But for building regular wood structures, I could go to Home Depot and come back with all the material later today to build a deck. That if you guys are all coming over on the weekend to build a deck with me, I could go buy all the material this afternoon.
And it would be done on Monday.
It would be done on Monday. We'd have it built very fast. There's a short lead time for stick frame construction because I can go buy all the materials. Obviously, that wasn't true during COVID. There was a real wood shortage, which meant that costs tripled for most instances of wood, but that seems to be settling out now. Concrete. I have to go in about 2 minutes here. So concrete, it's a composite material. That means there's more than one element or more than one material within it. So obviously we're talking about reinforced concrete. So we know we have steel and concrete. But the concrete itself is even a composite material. It's made up of stones, sand, limestone, and water. So there's all kinds of materials mixing together, and it itself is also composite. Concrete is good in compression, terrible in tension. Steel is great in tension. It's less good in compression just because it wants to buckle, but if you wrap it in concrete, it doesn't want to buckle anymore. So reinforced concrete, we're making the best use of steel and the best use of concrete combined together. With concrete, we have to build everything twice. First, we build a wood version of the structure. Then we fill it with liquid concrete. The concrete cures. And then we take away the wood structure. So what makes concrete usually the most affordable is the fact that we build with it the wood portion multiple times. Now, obviously, probably for a lot of landscape elements, that wouldn't be the case. We would just use it as formwork and then take it away. But in condos, for example, that's what makes it very cost effective, is that we reuse that formwork because they have the same floor plan on each story. So that means it's good when it's repetitive. It's slow construction. So if I said I wanted to build a concrete building, they could mobilize and be on site in a few days if they wanted to. But if you're building a whole floor out of concrete, you have to wait 7 days until you can start to take away the formwork and start to think about building the next floor. Where a steel building, you could build multiple floors a day if you wanted. It's, as we said, not very strong, so you need a lot of it to resist the load, but it's also that makes it very heavy. Even though it's technically lighter than steel, we need so much of it that it becomes a very heavy material to build with. And it tends to often be governed by its own self-weight. Oh, here's the important thing. For you guys, it cracks. Period. Just get your head around the fact that concrete cracks. Always tell every client, every contractor on day one, their finishes, their concrete will crack. I would say probably 50% of lawsuits are about cracked concrete. Structurally fine, nothing wrong with it, but it cracks, and people perceive a crack as a failure. Concrete is meant to crack. We expect it to crack. We do things to help control the cracking, but it cracks. And so as long as everyone understands that, we'll be fine. So let's start talking about the different elements that you guys might encounter in your career now. So I had a list at the beginning. I made this lecture. Dave quickly glanced at it. Between the two of us, we've given we're giving 5 lectures this week, the courses that we regularly teach, plus a few other lectures that other people have asked us to do. So we're feeling a little, there's a bit of crossover, and we didn't both have time to review everything. So I've made these slides. When I leave, some of it might be a bit of a surprise to him. We'll see how it goes. So the first one is paving. Paving is rarely structural, but you might use concrete, and people see concrete as being structure. They just can't get their head around the fact that it is not always structure. Sometimes it's purely paving. So how do you, as the landscape architect, know when it isn't, or when it is structure? When is it not your scope anymore and you need to contact one of us to do something with it? And I would say the best way to think about it is it a frost slab? If it's a frost slab, it's structural. If it's not, it's probably landscape. So do you want to talk about what a frost slab is, Dave?
Sure. What I was going to say first, though, is that the challenge comes in the definition, the colloquial versus technical versus
that's true
contractual definitions, right? So Shannon's saying it's not structure because it's contractually not structure. It's not the structural engineer's job. It's your job. But that said, it bears load. It's made of concrete. It's structure. Colloquially, it's structure. Everybody would consider it to be structure. So
I have to go pick up our children from the bus stop.
Okay.
So we might film this in stages as well, so you might see small blips within this. But Dave's going to keep going for
I'll
a few
be the
minutes
small
here.
blip for the moment.
And you can slide your chair over.
Yeah. Okay. So, what is a frost slab? A frost slab is a slab that is controlled to prevent movement due to frost. So, let's back up again. You probably know very little about geotechnical engineering, but you are probably aware that ice cubes float when you put them in a glass of or in a cocktail. So, ice cubes float because ice is less dense than water. It's less dense because it expands as it freezes. If you have water ice, if you have water below grade and it freezes, it expands, it lifts the grade. So why is that a problem? Well, I mean, all the grade everywhere else is lifting. Why would we be concerned? Frost slabs, if you have a building exit, and that is a required exit under the building code. Then it needs to be a barrier-free exit. You can't have a step, which means that we've got to have a slab that meets the building that cannot move up and down as a result of frost. So what do we do for a frost slab? Well, we drop walls around the perimeter and we put an airspace underneath. By putting in it, and that way the soil that's underneath can heave and settle. It doesn't affect the slab. The walls are founded below the frost line, so frost penetration is only so deep. Generally, in our area, it's considered to be 1.2 meters or 4 feet. So the walls are below the frost level, and the soil can heave and settle as it sees fit. Because there's an airspace underneath it, now that slab is spanning. That is the thing that makes it structural. It was structural anyway. That's the thing that makes it the structural engineer's scope of work. Ah, interesting. There we are. Great. Okay, so we talked about frost. Actually, I'm gonna pause for a moment. I'll rejoin you. You won't even be aware that I was gone. All right, everyone, I'm back. I have my coffee. Cheers. So we're going to talk about curbs. We're going to talk about curbs to distinguish them from walls. Now you're very well used to what a curb is because there's curbs adjacent to roadways. A curb is like a little wall that is less than 2 feet tall, or less than 610 millimeters. If it's less than 610 millimeters, it is not a designated structure in the building code, and therefore it doesn't need to be engineered. Normal rule of thumb is the width of the base of the curb is about 2/3 of the height of the curb. So a 610 millimeter tall curb would need to be about 400 millimeters wide at the base. Often they're tapered, which is why you only see 200 millimeters at the top. You also don't need a guard on top of a curb necessarily. Guards are required in the building code where there's more than 2 feet or more than 610 millimeters of elevation differential. You would need a guard. Landscapes are not buildings. There are conditions in landscapes that are hazardous. You're not obliged to put guards everywhere in a landscape, but often the building code is used as an appropriate standard against which to build, to design. And I think there's a general rule that may not be codified that if you invite someone to a place, then you need to make it safe. So if there is an existing condition that is a hazard, there's a cliff face, for example, that's not your problem as a landscape architect unless you build a trail to the cliff. And if you build a trail to the cliff and you invite someone to the place, then you have an obligation to make them safe. For things that are not structural, which means things that are not subject to loads that would make them have to be designed for compliance to some standard, curb, for example. Typically your top consideration is control of cracking. So for curbs, we don't put rebar in them to make them strong enough. They're as a lump of weight, they're strong enough. But we might put rebar in them to control cracking. We would put jointing in them to control cracking. I talked about frost slabs already and that it's typically about accessibility. What I did not say is that where an exit is not accessible, we have a door threshold, we have grade. Grade is going to move up and down. What we can't have is the grade moving up and blocking the door. So if grade moves up and down and is generally 100 to 200 millimeters below the door threshold, that's not actually a problem unless you're in a wheelchair. So if it's barrier free, that's different. But if it's an exit at the bottom of a stairwell, for example, we would simply put a step. And then the grade can move up and down as it sees fit. It's not a problem. It doesn't present a hazard. Here are some examples of frost slabs. This first one is the one I described before. It's void formed. So walls that go down below the level of frost penetration, and then an airspace underneath the grade. This is the most robust way to build a frost slab, but it is not the only way to build a frost slab. This example down below here, we have insulation under the slab rather than a void space. If we can prevent this ground under here from freezing, then we can prevent it from heaving. We need to take the insulation out far enough beyond the edge of the slab that the total distance to the soil under this edge is larger than the depth of frost penetration. So in this particular example, if we add up the vertical distance of 400 millimeters plus the horizontal distance of 1200, it's roughly 1600 millimeters from the ground surface to here, and that's enough to prevent heaving. There used to always be a rule that 1 inch of insulation was equivalent to 1 foot of soil. So that if we wanted to do the work of 4 feet of frost cover, we would need 4 inches of insulation. That is a nice round number. It's very convenient, but in fact it's very conservative. If we actually look at the conductivity of soil and compare it to the conductivity of rigid insulation, extruded polystyrene like styrofoam SM or something, we'll find that 2 inches of rigid insulation is abundantly less conductive than 4 feet of soil. And so 2 inches is a fairly common standard now. And so you can see what's happening here is that this slab sits on grade, but this grade is protected from freezing by the insulation, and therefore there's nothing that tends to make it heave. This doesn't work everywhere. So we're doing a project in Winnipeg right now that's on all the soil in Winnipeg is expansive clay, and that clay is going to move up and down, or the ground surface is going to move up and down with changes in moisture content in the soil regardless of frost. And so we can't do a detail like this, or it's inadequate. Exterior stairs. So Shannon's simple rule. Does it act as a frost slab? Do we need to prevent it from heaving because it abuts something and it can't move relative to that thing? Now, if it's a stair, it's not about accessibility, obviously, because it's a stair. But it may very well be a stair in conjunction with a ramp or something. So if it needs to be a frost slab with a void under it, then it would be considered to be a structural scope. If not, it's really just paving, and we can just follow the profile and treat it like a slab on grade, a paving slab on grade. Excuse me. So here are 2 detailed examples. This is a paving condition. We have a little stair. It's all poured integrally. We embed it down at the bottom. We put a little bit of insulation under to minimize or manage the potential for movement. Let's talk about retaining walls. As landscape architects, a thing that you're going to do a lot is build retaining walls. So what we're looking at here is a cantilever retaining wall. You can see that the reason it's called that is because we have a wall that cantilevers up from a footing. Some simple rules of thumb. we want the footing to the extent possible to be under the high side of the wall. The weight of the soil helps to resist the tendency of the wall to overturn. I should back up and point out that soil is a bit like a fluid and exerts a lateral pressure like a water in a tank. It's not completely fluid. Generally, whereas water, the lateral pressure is equal to the vertical pressure. With soil, the lateral pressure is roughly 1/3 of the vertical pressure. But it does tend to behave a little bit like a fluid. So we stand a wall up and we backfill on one side. That soil is trying to push the wall over, which is why we put a fat footing down underneath it. And we put the footing under the high side because the weight of soil assists in resisting the overturning. Where we can put the footing under the high side, the proportions tend to be about 1 to 1.5. So if we have a 6-foot tall wall, we need about a 4-foot wide footing. Those proportions are about right. Remember when I told you that a curb, 1 to 1.5 is about the right proportion. So that sort of follows through. If the footing is on the low side, so I should back up here. If we are in a fill situation, it's no problem putting the footing under the high side. We can put it on either side. If we are in a cut situation, so the grade is high and we're trying to cut a ramp down into it, putting the footing on the high side means we have to make our excavation much bigger. And often we will, and we may very well be up against a property line or something. So often in that case, we would put the footing on the low side. On the low side, it's much less efficient. And so where our rule before was 1 to 1.5, if our footing is on the low side, it's more like 1 to 1 because we don't have the weight to hold it down and keep it from tipping over. In addition to managing overturning, which the wide footing does, we have to manage sliding. There's a lot of force on that wall and it wants to slide. On this particular diagram, the sliding is managed by a combination of friction on the bottom and passive earth pressure on the low side. So what is passive earth pressure? Active earth pressure is if the earth is pushing on you, that's active earth pressure. If you are pushing on the earth, that's passive earth pressure. Now, you may wonder, what difference does it make? Well, it makes a gigantic difference. Imagine standing a shovel up and someone piles soil on one side. Well, you can imagine you can hold that shovel up with one finger. It makes almost no difference. Someone piles soil. Now take that shovel and stick it in the dirt and try and drag it through the dirt. That's passive earth pressure. If you are trying to move the dirt, the force is very big. If the dirt is trying to move you, the force is quite small. So passive earth pressure on the low side assists in resisting sliding of a retaining wall. Drainage. Drainage is important for retaining walls. I mentioned the soil acts like a fluid and pushes laterally, like fluid in a container. If we have fluid behind the wall, that adds to the force, and it adds significantly. So we want to drain the water away from the back of the wall. So here's a few different types of retaining walls. This is a gravity wall. Now these rules of thumb are slightly different than the ones that I just gave you, but they're close. So this is what we would do as a curb. They're saying it's a 2-to-1 ratio. You know, they're probably not wrong. It's just a little bit less conservative than I'm used to. Cantilevered retaining wall, 0.6 to 1. So that's about what I was saying, same, just about 1 to 1.5. Here on the low side, they're saying 0.7 to 1, 1.25 to 1 with surcharge. So what is surcharge? If we put load on the high side of the wall, that's surcharge. And the more force we put on top, the more it pushes sideways. I don't think to distinguish that because we always have surcharge. We always consider an outdoor public realm to be 100 pounds a square foot or 4.8 kPa of surcharge. So we would design for that without thinking about it. If there is a roadway adjacent, we would design for 12 kPa surcharge. And 12 kPa assumes that there's a fire truck. There's a different type of retaining wall. This is called a timber crib retaining wall. You've probably seen tons of these things around. You've probably seen almost all of them that you've seen are probably built incorrectly. And that's why probably most of the ones you've seen are tipping over. Because people tend to neglect the dead man and the tie. So we need to take a tie element back periodically to what's called a dead man, which is just a timber buried in the ground. Well, kids are home. I'm going to pause here, say hello to my kids, and then come back to you. Okay, back again. So timber crib retaining walls. There are other types of timber crib retaining walls, but this is the kind of most common vernacular construction. Modular block retaining walls. So this is something that these things showed up in the 90s as an engineered solution that used self-weight or geotextile fabric. So you can see up at the top here, there's nothing other than its own self-weight that's holding it and resisting lateral loads. The farther down we get, we introduce geotextile fabrics. This is literally a sheet that's got tensile capacity that's just held in place and with friction in the soil. And the farther down we get, the more often we need the geotextile sheets. I'm going to point out here, this is called a batter. A batter is the angle of lean on a wall. May not seem all that significant, but the farther back you batter the wall, the less earth pressure it has. To the point where if you're at about 7 vertical to 10 horizontal, like just about the pitch of a stair, there's no earth pressure at all. At that point, the soil is self-supporting. So even a relatively minor batter makes a big difference in the force. The other reason we batter a wall is because active earth pressure depends on movement. So I said the active earth pressure is very low. It is, but it's only low if it can move just a little bit. It doesn't have to move a lot, but it has to move a little bit. If it can't move at all, then we have what's called at-rest earth pressure, which is higher. So what we do with a cantilevered retaining wall is we let it move a little bit. If it starts with a batter, earth is pushing this way. If the retaining wall starts with a batter on it, it moves a little bit, it gets more vertical. And no one will be troubled by it at all. If it starts perfectly vertical and moves a little bit, now it begins to overhang and looks like it's dangerous and about to fail. So always good to batter back a retaining wall a little bit. An example of a modular block retaining wall. I meant to grab a picture of a dry stone retaining wall, but you can Google a dry stone retaining wall. Dry stone retaining walls, the structural behavior is very much like a modular block retaining wall. It's just done with natural stone and is a more artisanal process. It takes someone who knows what they're doing to build a dry stone wall properly. Whereas a modular block retaining wall, if the keys align, the blocks are keyed together and it's going to be fine. This is a gabion retaining wall. A gabion is a big basket, about a meter by 2 meters long, of woven wire. Is it woven? No, it's twisted wire. It's like chain link, twisted wire mesh, and then filled with stone. And it's a gravity retaining wall, the same as the other ones. Once again, it relies on a batter. The interconnection between the gabions is purely friction. This one looks particularly nice. Gabions are not as easy as they seem. We don't just dump stone in them out of a bucket. A gabion wall, the stone needs to be hand placed for it to look this good. It's also just a little bit artisanal if you want them to be done well. This is an armor stone wall. This is not the same as the dry stone wall that I was just mentioning, but you can see that the principle is the same. It's a gravity wall, meaning that the individual elements are heavy enough to resist the lateral earth pressure without overturning. Oh, here we are. There's our dry stone wall. Give you a sense of proportion. You can see that minimum batter of 1 to 6 is what's recommended, which winds up giving us a height to width ratio of about 1 to 1.5, which is what we had talked about previously. Let's talk about posts. Posts do not sound very exciting, but as a landscape architect, you're going to design lots of posts. You're going to design posts for fences. You're going to design posts for light standards, for flags, for pergolas and pavilions. So we can talk about the general criteria for posts. Tall posts are often governed by wind. So wind blows on a post, you think, oh, it's a little post. How much wind can it take? But often there's an object on the top of that post. It might be a light fixture, it might be a basketball net, it might be a flag. We have what's called an EPA, which is effective pressure area or equivalent pressure area. That is essentially saying that we've got this light fixture of complex geometry. It's been wind tunnel tested, and we've demonstrated that its wind resistance is about the same as a 500 millimeter square board. And so we use that to determine the amount of wind load. In addition to wind, we typically design a post for a live load. This is the load of somebody climbing on it. Shannon likes to talk about the one drunk guy load case. This is if you build something that someone can climb on it, during the life of the structure, someone will climb on it. And so we typically design for 1 kilonewton. 1 kilonewton is the weight of a heavy person. And we apply that at any point to the worst effect. And then, of course, the last load that we need to deal with is self-weight. So how are posts anchored? This is a free body diagram. I hope that you guys have at least a sense of what a free body diagram is. A free body diagram is a diagram that shows all the imposed loads. Let's have a look up here. We have axial load, self-weight. We have shear. This is the wind that's pushing on it. And we have overturning because the base is here and the wind is up here and the whole thing wants to rotate. These are the imposed loads. These are the resisting loads. So we have a passive pressure triangle here and a passive pressure triangle here. In order for that post base to rotate, it needs to push the soil at the top this way and the soil at the bottom that way. Passive pressure in both ways. We have friction on the side. So you sink a post in the ground, and the ground will try and grab it. And then the bottom sits on soil or rock. So this is, we often refer to that in our local market as a caisson. I'm not sure why in our market we call it a caisson. Most places call it a drilled pier. which kind of makes more sense. So you drill a hole or auger a hole and fill it full of concrete, and anchor your post to that. Our alternative is a spread footing. So we can do the same thing with a spread footing that we do with an augered pier. In this case, it's friction on the soil that resists the lateral pressure, and the tendency to overturn is simply resisted by an eccentric bearing pressure that one can imagine. If you're standing on your 2 feet with your legs spread and someone pushes on you, all your weight goes to your kind of downhill foot, and that's a little bit what's happening with a post on a spread footing. So here are a few examples with a post can be embedded all the way down to the bottom of a sonotube. Sonotube, by the way, the technical term is a drilled pier. Sonotube is a circular cardboard form for pouring concrete. Now, we're sinking it into the ground. Why are we worried about sonotube? Why would we form it, not just fill it with concrete? I'll tell you that in a second. But we typically use a sonotube at least within the frost penetration depth. Fence post, basketball net, these are essentially the same. Outdoor table. Now this is one that's subject to larger forces, and we've put some reinforcing steel in. If we are putting reinforcing steel in our sonotube, the post doesn't need to go all the way to the bottom. We just transfer the bending from the post into the drilled pier. Another detail we could have shown is a base plate and 4 anchor bolts. So when you're driving down the 401, you can see you've got giant light standards. They're not embedded into the foundations. There would be a circular array of anchor bolts, and there'd be a big base plate, and that's how the forces get transferred. So French fence post. Interesting. I'm just looking at the diagram on the left, figuring out where that came from. It says not code, done lots. So let's interrogate what is going on here. First off, I don't think fences are covered under the building code. Certainly I'm not aware, and they don't have details. Typically at the bottom of a fence post, you start with 6 inches of gravel. What that does is allows the water to drain away so that it doesn't wick up into the fence post and rot the bottom of the post. And then we have an embedment depth roughly equal to 1/3 of the post height. So 6 foot post, 2 feet embedment, 4 foot post, 1 foot 3 inches of embedment. So height divided by 3 gives you roughly the embedment you need. The diameter of the sonotube is just enough to get concrete passed all the way around. So we have a 4x4 post on the diagonal. That's going to be 6 inches on the diagonal. We want, say, 1.5 inches concrete cover. It would be a 9-inch or 230 millimeter sonotube is what you'd need for a 4x4 post to get concrete around it. So I said, why do we bother with a sonotube? It's so that this doesn't happen. So what's happening here is that every winter you get frost in the soil that grabs onto the sonotube. It heaves, lifts the sonotube slightly. Soil sloughs in underneath so that when the soil subsides, the sonotube can't go down all the way. And so it moves up a little bit. And over the course of a decade or 20 years, this is what happens. It's moving up a little bit every year. And they call this frost jacking. Frost jacking happens because of adhesion heaving. So we can have heaving from the bottom. That's the regular heaving. Heaving from the sides is called adhesion heaving. So adhesion heaving resulting in frost jacking. So we put a sonotube around that. Now the sides of the concrete are smooth. Now we have a sonotube of cardboard, which eventually just rots away, but we wind up with a smooth side on our drilled pier, and we don't get adhesion heaving. Let's look at pergolas and shade sails. One of the things you're going to do as landscape architects is design shade. Shade is increasingly a concern with global warming and sensitivities to melanoma, so we all want shade. These are some examples of basic shade sails. So shade sail is HDPE knit fabric. It's generally not watertight, but it's sufficient for shade. It's often on posts, as shown here on a fence. The forces can be really quite enormous for a shade sail, and we shouldn't underestimate them. Notwithstanding that they're often done this way, we shouldn't underestimate the size of the forces. And then canopies and pergolas. This is one that Shannon engineered at One Bloor on the terrace, and it was designed by Janet Rosenberg's office, I believe. And this is IQ Park, again, Janet Rosenberg's office. So a different solution. What's interesting is you can see how transparent this is to overhead light, and yet late day sun with the sun at any kind of angle becomes completely solar opaque. I'm going to just point this out. This is a very vulnerable detail, notwithstanding that we do this all the time and architects really like it. The coating on the column down here at the base is vulnerable to salt and to scuffs and due to shovels and everything else you can imagine. What we try to do is lift the base of a column on a little pedestal if it can be tolerated. If it can't be, we feel like we need to advise an owner that that they're going to have a maintenance situation. This is an amphitheater. This is a tensile fabric project. This is one that I designed a few years ago at Bronte Park in Oakville. So this is tensile fabric, not a shade sail. Difference is that this tensile fabric has a strength of something like 500 pounds per inch, or like 2 kilonewtons in two and a half centimeters. Extremely strong, and as a result we can have big membranes like this that can stand up to the wind and snow right on Lake Ontario all year round. They don't take this thing down. Tension structures are characterized by their boundary conditions. So this big mast with these big cables anchoring it down to the base. There are big forces in these, but they look beautiful, and particularly in a context like this where you're right next to a public marina, it looks like it belongs in a marina. Okay, some tips. This is Shannon's pet peeves. I'm going to share them with you. If you have something on a drawing that is structure, meaning that it is within the scope of work of the structural engineer, do not call up the scope of work on your drawings and then say refer to structural. If it's on the structural, don't call it up, because at least 50% of the time your drawings will then be in conflict and you're inviting an extra. If it is not structure, that is, if it is paving or if it is a curb or something that is not a designated structure under the building code that requires it to be engineered, then you as the landscape architect need to call it up. You need to call up the amount of rebar that it needs for crack control and whatnot. And you do not say refer to structural. So either way, if it is structure or if it isn't structure, the peeve, the takeaway is do not say refer to structural on your landscape drawings. If it is on the structural drawings, it's on the structural drawings. And if it is not on the structural drawings, then you'd better not refer to structural. Okay, so here's a few details. So you can see some, this is the context of this must be IQ Park, because there is our detail at the top of our drilled pier with our footing and our anchor bolts. This is something engineers do frequently, is we dash in elements that are not our scope of work, but we feel are important to describe context. So the reason this drilled pier is here is to support that post. Even though we may not be designing the post, we need to acknowledge that it's there so that the installer understands why he's putting a drilled pier there and know where to put it. So here are two types of foundations, one with a base plate and one that's buried. This is a boardwalk. This is a nice little detail. So here we have a swale condition. All the way down the swale, there's intermittent drilled piers, little posts, a few continuous beams, and a continuous boardwalk, which I think was metal bar grating to allow water and things to go right through. Guardrail on one side, because on one side, the height above grade is more than 600 millimeters. On the other side, the height above grade is less than 600 millimeters, and a guard is not required. One strategy you can take away from that you can kind of park for later is if you don't wish to have a guard, then berm up and make sure that you don't have more than 600 millimeters of height difference, and then you're not obliged to have one. This is another strategy for a frost slab. This is actually probably a transformer or something. Another strategy for a frost slab. See what we've done here is it's filled completely with clear crushed stone, and we don't have an airspace. So you may say, well, if we don't have an airspace, isn't it vulnerable to heave, since frost can go directly through there? And that is true. Except that, for one thing, how does water get in there? Water can't get in from above, and waterborne water can't wick up into this zone because it's clear crushed stone. So, little sidebar, we're going to talk about how water moves. So, water can move by water pressure. I mean, if we have a reservoir with a hole in the bottom, it's going to push the water down and into the soil, and then it's going to migrate out because it's under pressure. But water can also move by capillary action. So, in one hand, the water is being pushed from behind by other water. On the other hand, capillary action, the water is pulling itself along. And that's because water is sticky. It sticks to stuff. And it's attracted to surfaces, and so it's always going to pull itself along a surface. So water migrates by capillary action, but the capillaries need to be small in order to get the water to move. And clear crushed stone is considered a capillary break. The water won't lift through clear crushed stone. If that's full of sand or clay or something with a fine material, you saturate the bottom, the water will pull itself up to the top and then be vulnerable to freezing. Fill it with clear crushed stone, it's a capillary break. The water will not migrate up through clear crushed stone because the voids are too big. So we backfill in with clear crushed stone. Water can't get in from below because it's a capillary break. It can't get in from above because there's a slab, and therefore, even though it freezes, it's not vulnerable to heave. Now, I just said something that I hope that you will call me on. I just said water can't get in from above because it's a slab. Do not ever believe that a slab is waterproof. Slabs are not waterproof. Concrete cracks, and water finds its way through. If you need to prevent water from getting underneath something, you need to put a membrane on it. That said, in a condition like this, the amount of water that goes through is not significant. So we get a small amount of water through. It just works its way down through the voids in the clear crushed stone, and we will not have heave. Some other details. So this is a standard treatment of a stair. This is a frost protected stair because it has an adjacency that needs to be protected from frost. This is a walkway or a bench, similar condition. This is frost protected. Here we've got a big retaining wall. So this is an elevation of the retaining wall. Here's a section through our retaining wall. A number of things to note. One is you can see that this is a fill situation. So we put most of the footing on the high side. You can see that there's a slope here. That slope is actually meaningful. The steeper the slope is, the more earth pressure there is on the wall. So typically we consider the grade at the top of the wall to be flat, but that's not a guarantee. And if it is not flat, then it affects the amount of earth pressure. There's a swing gate in this case. So the gate, we would consider one drunk guy. We put 1 kilonewton right on the tip, and that would determine the amount of overturning on our drilled pier. So a number of other conditions, all frost protected slabs. This is actually interesting. So here we got a little wall retaining earth. Doesn't have our standard cantilevered wall footing. Here we got a wall retaining earth. Doesn't look like it's retaining much more. It does have a cantilevered wall footing. So what gives? Well, we consider any wall that's retaining less than 600 millimeters of earth to be not a retaining wall, and so we put it on a nominal footing. As soon as it's retaining 601 millimeters of earth, we consider it a retaining wall, and we actually have to do the calculation. I've always meant to derive a transition formula for walls that are retaining between 600 and 1200 millimeters of earth, so we don't immediately jump from no footing at all to something wide, but I haven't done it, and it just doesn't seem to matter all that much. Okay, so let's think about our takeaway tips from today's lecture. Structures are governed by strength, stiffness, and stability. Strength relates to non-recoverable movement. So that could be fracture, it could actually break, it could just bend permanently. Those are strength failures. Strength failure generally is associated with life safety. We say life safety, it makes it sound very dramatic. Often it's not actually life safety, it is the risk of damage that will require repair and cost money. That's what we're trying to control with strength, even if it's a perfectly safe condition. Stiffness, how much force it takes to deform a thing by a specific amount, and that relates to comfort. That can be comfort walking on it. You don't want to feel it vibrate. That can be the amount of drift. You may not want to see your pole flexing in the wind like this. Or visible sag. You may not want to see a sagging beam next to, if you can sight along it and see the horizon and behind, that makes it obvious. So it's physical comfort, it's emotional comfort, it's aesthetic comfort. And then stability. Stability is tipping over, it's buckling, ponding stability. If something can accumulate water, you get a feedback loop. Stability is characterized by a feedback loop.
Hi everyone.
Loads on structures, generally they come from the code, but not always. And so where there is not a published load in the building code, then the engineer uses discretion. our duty of care as engineer is to do what a reasonable engineer would do in the same circumstance. So we conceive the likely worst scenario, the worst thing that would happen in the lifetime of the building. We designed for that.
Hi, Dad.
Well, that is well timed.
Hi.
Okay, come up and say hello,
Hi.
and we'll finish up this lecture. Okay, buddy.
Oh, look at me, Dad.
I know, there you are. You're so
Okay,
handsome.
say bye to all the students.
Say bye, Duncan.